Okay, so in chapter one, we began with just sort of the basic ideas behind statistical studies. And sort of the goal was just to have kind of the language of statistics down. We've got that out of the way. We're going to do a chapter now that's on descriptive statistics. Which is chapter 2. Okay, and then in chapter 3 we'll start probability. Okay, so descriptive statistics is we talked about it a little bit, but this is just where we try and find ways to summarize large sets of data. So the first thing we do is a bar graph that's called a histogram, and then after that we'll do averages and then measures of spread. I don't know that we'll get that far today, but let's see how far we can get. Okay, so the first thing is it's asking for what's called a frequency table. Oops, I did not mean to do that. Disney Channel. There we go. Okay, so frequency table is just a table where you put values into classes, or sometimes they're called bins. So we've got the same randomly selected adult women that we did a dot plot of last time. But this time we're going to make a frequency table, then a histogram. So what we're going to do is, first of all, figure out the range, which is the distance from the lowest value to the highest value. So this is called the range, but it's just the max minus the min. And so you have to unfortunately scan through this. I think the max is 184, and I actually remember that from last time when we did a dot plot. So the highest value I think is the 184.1. Does anybody see the smallest value here? I see a 148.
Oh.
Is that it? The 148?
Yeah, it looks like it.
Okay, so that's the min, hopefully. And so we'll just subtract. This just tells how wide the data set is. So 184.1 minus 148. I want to say it's 36.1, but I'd rather you guys helped me. I should have a calculator sitting here. So I'm scrambling to get a calculator real quick.
I got 36.1.
Great.
Me too.
And I got a calculator. So that's the range, 36.1. And then we're going to make classes, as you can see down in the table down here. A class is just going to basically say, okay, from 10 to 20, 20 to 30, like that. So the class widths are just going to be how far from one class to the next class, basically. So what you do is you take the range and you divide by the number of classes. So the range is the total width of a data set, and then you're going to divide that into the number of classes. Okay, so however many classes you can fit into the range. So here, the range is 36.1. And then if you look up above, it says that there are 5 classes. Okay, and we usually do 5 to 10 classes. But this time we're going to divide by 5. And then you actually have to make this a little larger. So what'd you get for this?
7.22.
Yeah, so 7.22. And then I'm going to say that you always have to make this larger. Just a little. Oops. Okay, because if you don't, it'll end up not covering the whole range. I know that's weird. So I'm going to round this up to 7.3. And you should do the same number of places as the data. So I'll make a note for that too. So, right, our data have one place after the decimal. So this class width should also have one place after the decimal. So even though the natural rounding for 7.22 is 7.2, you have to make it bigger, or the classes won't add up to the whole range, and you will always end up with a value that misses, that doesn't fall into a class. So you have to make it bigger. You should sort of just making it swell a little bit so it can just cover the whole range. Okay, so again, the rounding rule is to round up to a larger number. With the same number of places as the data. Okay, so any questions about that? Okay, so then the min was 148. I'm going to start at 148. Okay, and then from 148, I'm going to add.
Well, I have a question.
Yeah, go on.
What do you mean? So I understand the rounding rule, but like, what does it mean? Number with the same numbers of places of the data. What is that?
As the data. So the data have one place after the decimal. The data would be the data you're summarizing. With one place after the decimal here, I should also round the class width to one place after the decimal. So 7.22 has two places. You should have one place, and you should make the number larger. Does that all make sense?
Because what you're saying is all the numbers up here, like 156 to 162.3, they only have one number after the decimal. So you want
we call those place values, yes. So we just say places.
got it. Okay. So if they had two, then we would want the answer to have two.
Yeah. Yeah.
Okay.
You want to match the same number of places after the decimal.
Okay. Thank
Okay.
you.
No worries. The first one, 148.0. And then to go to the next class, I have to add the class boundary. So to 148, you need to add 7.3. Like that. And so you get 155.3. And then do it again. You get 162.6. Do it again. 169.9. One more time. 177.2. Okay. Any questions? Now, those are called lower limits for the classes. Each class should also have an upper limit. And the upper limit for the first class should be one value below 155.3 to the nearest tenth. So what would go below 155.3 to the nearest tenth? So you want to say 155 point, not 0.3 because that's an overlap. These should be non-overlapping classes. So 155 point,
2.
yep. So you're just going to knock one digit down for the upper limit of each class. So the next one's going to be 162.5. Okay, then 169.8. Okay, and then 177.1. And then, of course, we're hanging off a cliff here for the last one because it's not clear what the last one should be. So I'll just note that once again, to go down in the table, you have to add 7.3. So I'll write plus 7.3 here. So 177.1 plus 7.3 is 184.4. So these classes are all the same width. Okay, so any questions about that? So we're adding 7.3 as we go down the table, not across the table. Okay, now we just do tally marks. So generally what we would do is just start crossing values off as we put a tally mark for the in the class that each value falls in. So first one's the 158.6 that goes in the second bin or the second class. So I just put a tally mark there. And then a 170.4 and so on. That's the third class. Okay. The goal of this is to get a sense of how the values are distributed. This is not an even distribution of values across the range. There are certain regions in the range or classes that are more probable. Okay.
About 164.
Sorry?
Why did he leave out 164?
I didn't mean to. So you guys, how many did you get in the third class? Did you guys get 5?
I got 5 in the third one, and
Okay.
I have 16 in the second.
Yeah, that's what I have.
Okay.
So 164 I did miss, so I'll add that. No good explanation for that other than it happens. Okay, any questions? Okay, so 5, 16, 5, 3, and 1. We can go ahead and do a total for that. So 21, 26, and 4 is 30. Okay, so there were 30 values. That's the total number of values. It's called the sample size is what we're called. Sample size, meaning that we have 30 values in our sample. Okay. Now, if we were to do relative frequencies, we would take the frequency of each value or each class and then divide by the number of values, which is 30. So the first one you'd say 5 over 30, then 16 over 30, and so on. And then usually we would convert these to proportions or to percentages. So when we say proportion, we usually mean a number, just a decimal between 0 and 1, not a fraction, but a decimal representation. So real quickly, I think I probably could do some of this in my head, but 5 divided by 30 is 0.167. And 16 divided by 30 is more than half. So that's 0.533. You can see I'm keeping 3 places after the decimal. That'll be my rule for probabilities. I don't feel like making the rule yet, though. We got a 5 out of 30 again, which is 0.167. 3 out of 30 sounds like a tenth to me, so that'll be 0.100. And then 1 divided by 30 is a third. Try 3.33%. So 0.033. And since I said percent, let's go ahead and give so we call that a proportion representation, a number in decimal between 0 and 1. So first representation I wrote was a fraction. Second one was with proportion. The last one will be a percent. So 16.7%. And you're just multiplying by 100, which moves the decimal place 2 to the right. So 53.3%. Okay, 16.7%. And then 10.0. And 3.3%. Those are relative frequencies. And relative frequencies will be used pretty soon to estimate probabilities. So the middle class had 16.7% of the data. So the probability of a value landing in the middle class randomly is going to be estimated at 16.7%. Any questions? Hey, what do those percentages add up to?
100.
Yeah, so these will add up to 1, plus or minus a margin for error. We're rounding, and rounding introduces error. So they should add up to 1 or 100%, or 30 out of 30. is the total. So again, these decimals have all been rounded, so you can kind of figure sometimes they won't add up to 100%, but it'll be close. Okay, within a rounding error. Okay, any questions? So that's called frequency table, and that's one way. And you can kind of see the histogram there. So the histogram is just the bar graph that we're making next. So histograms are sort of sideways bar graph, or sorry, frequency tables are sort of like sideways bar graphs. So I just have to make those bars. Okay, any questions? But then the markings, the class boundaries get to be the markings on the number line. So we have to do class boundaries real quick. If you just, what you're doing here is the midpoint between lower and upper limits for subsequent classes. I'll say consecutive classes. Okay, so if you just look at a lower limit and an upper limit, real quick, I'll highlight the upper limit and the lower limit for the next consecutive class. So we're trying to find the midpoint between 155.2 and 155.3. And the easiest way to do that is just to add a 5 after the 2. So it's just a 155.25. And the next one is 162.55. Oops. And the next one's 169.85. It's just a single value that divides the classes, and that works better for a graph. 177.15. And then 184.45. So all I've done is taken all the upper limits and added a 5-digit after the last digit of the number. And then there should also be one before the first class. So here you want to subtract the 7.3, which is the class width. So here I'm going to say minus 7.3 here to get the earliest one, and I'll do that in red. So if you take the 155.25 and subtract 7.3, it's 147.95. These are all 7.3 apart. So the first one is 147.95, I think I said. Okay. And then those become the markers on the histogram. And I'm going to try and squeeze that in. I actually feel like just copying and pasting. This is going to be a little lazy. I feel bad. Not that bad. And I didn't give enough space clearly. And I need to spread them out some.
Can
So
you please define what an upper limit and lower limit is?
Yeah, for each class. So the classes have an upper limit and a lower limit. But when you do a class boundary, oops. I'll do that in plural, lower limits and upper limits. So when you do a class boundary, you're sort of averaging the upper limit of a class with the lower limit of the next class to get a divider between them. Is that all right?
So right now you only focused on the upper limits for the list
Yeah,
of numbers.
because I mean, the bottom line is if you just check it out, if you average those two numbers on a calculator, if you add 155, now let me just wave here. If you average the 155.2 and the 155.3, you get 155.25, which is right between those two numbers. But the easiest way to say it is put a 5 at the end of the 155.2. So all I did was just put 5s at the ends of all the upper limits. And that gives a value between the two classes.
Is that all that we use? Just always out of 5?
It always works like that, yeah.
Okay.
If you, anytime you average two consecutive numbers, like a 4 and a 5, what's the average?
4.5.
Exactly, you're putting a 5 after the 4. You follow me?
Yeah.
That's just what happens. So it's, you know, if that helps you remember what's happening there, that's fine. You're just averaging two numbers. To get these midpoints, and now you can see I've down below, I've attempted to plot all these midpoints, these boundaries, I should say, on this number line down here. This is going to be our histogram. So here comes the histogram. See if I can pull this off here. So the first class has 5 values. So I'm going to try and draw a rectangle that goes up to 5. Like that-ish. I think I'm good with that. And I'm just going to kind of paste this and change the size of it over and over. Next one goes up to 16.
Professor, you put the first one up to 7, I believe.
Oh, good call. Thank you. I will fix it. But I'm having trouble with the second one. Why am I having trouble? Close enough. Okay, this guy is too tall. Sometimes the iPad, it just runs really slow. Okay, this guy I'm gonna just copy and paste over here. And then I have to do a 3. Like that, I guess. And then a 1. Something like that. Sometimes we might help to put the numbers on here, you know. So if you think it's more readable, 5, 16, 5, 3, 1, nice little bar graph gives me a sense of how the data values are distributed, which is really important in statistics. the shape of the distribution tells you what tools you can use to analyze the data. Okay, bell curve. This one's not really a bell curve because bell curves are symmetric. So this one's what's called skewed. I think I talk about that on the next page. Yeah. And then with a relative frequency histogram, it's the same thing. And unfortunately, that means we're going to draw this thing again, but I'm going to change the heights to the relative frequencies instead of the frequencies. Hope this works out. Forgive me from just pasting this. These are going to all be wrong, so I'm going to be correcting the heights. Okay, so the first one has a height, let's see, relative frequencies of 0.167. So I'm going to just go through and correct the heights of all these bars. And it's going to scale it, but it'll still be roughly the same shape. So 0.167 is going to be right about here, I think. Next one goes up to 0.533, maybe here. Next one's the same as that other one. Then a 0.1. And a 0.03. Yeah, this last one's going to give me a little trouble. That's fine. So again, I'm going to put in the frequencies. So 0.167, the relative frequencies, 16.7%, 53.3%, 16.7, 10%, and 3%, 3.3%. Okay, so that's the relative frequencies. Basically, it's the same, just using kind of percentages rather than actual the numbers, the counts or the frequencies. And I'll let you guys have a little moment to catch up on this.
Why do we need to convert to a decimal or a percentage for the relative frequency when we're not using that in the relative frequency histogram? What's the
Well,
point?
why did I convert them to a percentage?
Yeah,
Well,
like we're not using that in the graph at all.
yeah, the relative frequencies are bigger than the graph. They're going to be probabilities, and normally we want to be able to express probabilities either way. So as I had said before, that fourth group has 10% of the values. And so if someone said, well, what's the probability of being in the fourth group? Then you'd say, well, it's around 10% based on the data that I have. So again, the relative frequency graph is going to eventually turn into something called a probability distribution. And the areas are decimal values, but we always convert them to percentages. So the relative frequency histogram actually has legs, and it turns into something sort of theoretical eventually. Anybody else, anybody need more time on this? Happy to wait. Okay, it doesn't sound like anybody wants more time. So you can see I did a table of distribution shapes on the next page. So it's kind of nice if I get these terms out there. So just real quickly, let's label these as skew left. Okay, so it has a tail on the left. Okay, then skew right with the tail sort of going to the right. Okay, the flat one is called uniform. This happens sometimes. If you talk about like a distribution of phone numbers, if you were to sort phone numbers from low to high and talk about their distribution, I think you'd see a flat distribution with every phone number basically equally probable, at least in the range of possible phone numbers. I don't know if that's true or not. I'm making it up. Okay, any questions? So skew left, skew right, uniform. These, all of the bottom ones are bell-shaped. Okay, the first one's called, okay, there's some pretty nasty words here. The middle one is called mesokurtic. Like mezzo piano. Those of you that have done music know mezzo means medium. Okay, so mesokurtic. The one on the left is platykurtic. And the one on the right is called leptokurtic. And we'll be talking about a measurement called kurtosis later. Kurtosis is a measure of peakedness, which is basically how well defined the peak is in a bell-shaped distribution. So when the tails are short, they're called platykurtic, like a platypus. And you have one of the most famous statisticians drawing pictures of platypuses and two kangaroos that lep about for the leptokurtic. That's how William Gossett, also called student, remembered leptokurtic, because kangaroos lep. Kind of lame, I know it's lame. And then platypus is a beautiful picture of a platypus making a platykurtic distribution with short tails. Love that picture. Any questions? It's because it's so dumb. So the distribution names, if I ask you to describe a distribution, then these are the words you have at this point in your vocabulary. There's some others like bimodal and multimodal. That's kind of the only one I haven't covered here. That will come up later. Okay, any questions? Okay. I do believe that's it for that lesson. Now, I don't know if you can see this, but we've skipped 2.2. And if you look at the homework in Canvas, 2.2 is extra credit. So do with that as you will. If you like accumulating extra credit, they do help if you do lots of them. And just doing one extra credit problem is not that helpful actually for your grade. But if you want to stay on top of it and let it accumulate, then I think you'll get an accumulating benefit. Okay, so that would be all we're talking about 2.2. There's not really, it's sort of big picture stuff in 2.2, which we'll get to eventually. Okay, so any final questions about what we've just done with the histograms?
Are we supposed to know how to distinguish those like three bottom ones?
I don't see how you could distinguish them. No, I think you would just say that it's bell-shaped, but I still want the words out there for platycurtic, mesokurtic, and leptokurtic. And later on, we'll have a measurement called kurtosis. And it turns out if the kurtosis is a certain number, you say it's mesokurtic. And if it's bigger than that number, it's leptokurtic. And if it's smaller, then it's platykurtic. Okay. Oh, by the way, mesokurtic is also called normal. Glad that came up because I meant to put that there. So we have a one of the most important probability curves is called the bell curve, also called the normal distribution, and that's the one that's mesokurtic, and the one that's most often seen with large data sets. Okay, any questions? All right, then I think we can jump right up to 2.3. This one is on averages. So let's see how far we can get. This is a pretty easy lesson, 1 page of notes. So I don't think we need to spend too much time on this. So just a reminder, and again, this one's on averages, you can see, okay? So averages are primarily gonna be the normal thing that we call the average, which is technically called the mean. And then there are a couple other averages that are less important that we'll talk about. Okay, so a parameter this is a numerical characteristic of an entire population. Boy, what in the world was that? And then a statistic is a numerical measure of what? Anybody remember?
Summary?
Not an entire population, but a subset of a population that's called what?
A sample.
Sample.
Yeah, sample. Thank you. Okay, so every statistic that we compute also has a parameter that goes with it. And again, the statistic is the estimate of the parameter. The statistic comes from a sample, and it's used to estimate the parameter from a whole population. Okay, so then under notation, little n is going to be sample size. Big N is going to be a population size when finite. There are mathematically infinite populations. Like if you want to figure out what the average roll on a fair die is, a six-sided, singular for dice, then you can't roll it just 1 or 10 times to figure out the average roll on a die. That's a population of rolls that you could just do forever. So that's sort of an infinite population. When we talk about the population of tosses on an unbiased coin, that is also sort of an infinite population. And if you want to know the probability of getting heads, You just have to keep tossing and computing these things we call relative frequencies to estimate a probability. Okay, X represents each value. In the data set. Okay, when we do this Greek letter here, that's a Greek capital sigma. It means the sum of all. Something, okay? And again, that's a Greek uppercase sigma. Sigma is just the S in the Greek alphabet, and of course the S stands for sum, like you're adding things. Okay, and a sample mean is an X with a bar over it. Okay, remember X is every value in turn in a data set. So to compute X bar, we would sum all X, so it is the sum of all X in a data set, divided by the sample size, which we said was N. Okay, any questions? So that's the sample mean, an X with a bar over it. I think the bar reminds me of a scale. So it's like a balancing point on a distribution, the center of mass, if you like, of a distribution. And the sample mean is the center of mass of a distribution. Same formula that's used in physics for center of mass. Now the population mean is a Greek letter mu. So that's a Greek M. But it's just called mu. A lot of people say U. It's not a U. If it's a letter that we recognize, it's more of an M. Okay, so mu is the sum of all values in a population over the population size. I'm using a capital N. Okay, so this is when the population is finite. Okay, and just maybe for context, mu tends to be unknown. Because populations are big. So we estimate it with X bar. Now, strangely, I don't see myself doing the mean here. So let's squeeze the mean in on the example below. So the mean is going to be X bar. I'm in a tough situation. Obviously, we're not going to add this up by hand. So I think what we're going to do is I'll just type the formula down here, sum of X over N. And then I want to go ahead and start using Desmos. Okay, so I'll go ahead and say computations are done in Desmos. So that's www.desmos.com. Okay, so you just click graphing calculator. Okay. So right now in Desmos, that's funny how I didn't give much space here. So in Desmos, I want you to store these values in a list called A. So A equals square bracket, and then the list, the whole list, 148, 152.2, with 152.7. I'll say etc. And then you close with a square bracket. Okay, so I'm going to go ahead and very quickly pop over to Desmos. And you can sort of, I recommend you do the same thing, though I think you should type these in. I think you should practice this once. Okay, so let me go ahead and share my browser and go over to Desmos. Okay, graphing calculator. And so I'm going to make this really wide. We're not going to do any graphs, so I'm going to make this the graph real small here. And just say A equals, and then start typing. And when you hit enter, you should see that it's a 30 element list that doesn't all fit on the screen. I don't know if I can make mine bigger. I'm trying to make this a little bigger. I'll go wider that way. What if we did that? Still can't see, I made it as wide as I can and I still can't see the whole list. So that's just the way it is. But later on, we'll double check and make sure there's no mistakes if if we start getting different answers. You can click on this and scroll through it, which I am doing now. Okay. So any questions yet? Now, to get the total of the values there, I think if you just say sum, oh, that's not going to be great. I don't want to use that. So if I type, you're going to hate what I'm about to do. Sum, you don't need ever to do this. I'm going to go from 1 to 30 on A sub n. So that should give me all the values. No, I did that wrong. A n like that. I think we will. Okay, so I'm not going to ask you to do this, but I needed to know what the total of the A values are. This is A1, A2, A3. So this is doing AN, where n goes from 1 to 30 and adding those up. So the total should be 484.1. To get, if you want to play with that, you just type the word sum, but I'm not going to ever have you do that part. Okay, so the numerator, the sum of these should be 484.1. Did anybody get different from me?
So how do we sum it up then without putting all those symbols in?
Oh, 48. I don't have a way. If you don't want to do that, let me just show you again how I typed it. Okay, so I typed the word sum and it automatically changes to this. So there are 30 values in the list. So I'm going to have my index, my counter go from 1. And then if you click up above, you put a 30 up there. So you have a counter going from 1 to 30, and you just need to add a, and then in square brackets do an n, so that you're saying, okay, I want my counter to look at the nth element of a from 1 to 30, and just add those up. So if you hit enter, and again, I'll never have you do this again, but it should add up to 484.1. Can anybody verify that?
I got 481.8.
Okay, what, anybody else have something different?
I got 484.1.8.
4841.8 is what I got also. And then this should be divided by 30 to get the average. So if we do 4841.8 and then just type a slash and put a 30 underneath it, then you can see the average is 161.39. Okay, and we're going to round that to 2 places after the decimal. And I'll make a note for the rounding rule on this. Okay, but as it stands right now, in my notes, let me show you what I've written. Okay, so just to let you guys know, all I'm going to have you do to compute an average, this always happens. Hang on. Okay, so all I'm going to have you do to compute an average is just to write the number down, what the average is. So in Desmos, to get an average of all the values in the list, you type mean and then the list name in parentheses like that. That's all you have to do in Desmos. Mean of A. So let me go real quick to Desmos again. So again, just pretend like these last 2 things I entered never happened. I kind of want to forget what I did. so that you're not overwhelmed by it. I've typed in a list with 30 values. You have to do that. And then if you want the mean, you say mean of A, like that. And it gives the 161.39, which is what we got. Okay, and again, I want you to keep 2 places after the decimal, and I'll give you a rule for this in just a second. Just type the word mean and then A in parentheses, no spaces. Okay, any questions? Okay, so I'm going to pop back to the notes again real quick and define the next few averages. Okay, so for the mean, we get 161.39. You don't ever have to show your work computing the mean. I'm going to assume you're going to use a tool for this. Okay, the median is the central value after sorting the data set. I'll say the center value of a sorted list. Okay, now just real quick, an X with a tilde, this is not a bar, X bar is the mean, X tilde is a sample median. Okay, and then a mu with a tilde over it is a population median. Okay, so the central value of a sorted list. Now I have 30 values. This is actually a little more complicated than I'm saying, because if there's 2 central values, you have to average them. With an even number of values, there's always 2 central values. Now, if you look at this list, you'll see the 159.8 and the 159.8 are the 2 middle values, because it's the end of the first row, the beginning of the second row. There's the same number of values in each row, and the rows are and the data set is sorted from low to high. So the list has to be sorted before you pick the central value. If there's 2 central values, you average them. Here, they're both the same values. So when you average 2 159.8s, you'll get 159.8. So here, the X tilde is 159.8. Now, all the mechanics of how that's computed are described in the book, but you are not going to compute this by hand. Okay, not on an exam and not in your homework. All right, I want you to go back to Desmos and just ask for the median. This is not a class on doing arithmetic computations. Okay, so I know and you know that you can add up a list of numbers. I don't want to see you do it. I just want you to use a tool for this. So in Desmos, you say median of A, and you can see, I don't know if you can see over here, it's 159.8. Okay. So the hardest part is getting the list in. But once you have a list, this is super slick. Okay, it does way more advanced stuff than this. But this is just us beginning to learn how to use it. Okay, any questions?
What does the A stand for again?
A is the list name. You have to give your list a name. See up above, I said A equals the list.
So it could have been like B or C
Yeah,
or
I'll
X.
change it right now. I'll change it to C. And now there's an error message, see?
Mhm.
And now I'll change the A to a C. and there's my mean, and then the median I'll change to a C. So the list is, you can call it anything you want. It can only be one letter though. Don't give it like your name. Okay, it's got to be a one-letter name. Okay, I always use A, just to keep it simple. Okay, so you'll have homework where you have to do means and medians. Let's go ahead and go back to the notes real quick here.
Will sorted always be numerical order?
When you ask for the median, it automatically sorts it internally. So you do not ever have to sort the list. You follow me?
Yeah, I got it.
You
Thank
will
you.
never sort a list of numbers. You just ask it for the median, and then it goes through the process of sorting them and then picking the middle value for you. Okay? It's not impossible to do, but sorting it to 30 numbers takes forever. That's a drag. So just let the software do it. I know you can do it, and that's not what I'm trying to test you in this class. So, oops, wrong thing. Here we go. Okay, so I have my median 159.8. So the mode is the most frequent value in the data set. Now, you have to just find this yourself. So, let me put my median command down here for what I was talking about with Desmos. So mean A, median A. Okay, so for the mode, there is, I looked and there's no command for that in Desmos. Okay, so you're just gonna have to spot that yourself. Of course, I see 159.8. Does anybody else see a repeating number in the data set? It's nice when they're sorted.
I don't.
I don't either. Just double checking. Okay, so here, let's go ahead and just say this. Our data set has, that's hard to read, hang on. 159.8 as the only repeating value. So 159.8 is the mode. So that's not really a computation, it's just sort of scanning through a list.
What if there's small double numbers?
So you mean two things that repeat?
Yeah.
So a data set can be bimodal. A data set can be trimodal. A data set can be multimodal. Okay. And so if you want, you can make a note of that. Data sets can have more than one mode if there's a tie for first place, basically. Okay, so the mid-range is super easy. This is the max plus the min over 2. You're just averaging those. So here, the max is 184.1, but if the data values aren't sorted, I'm going to pop over to Desmos again real quick. So it's easy to see the max when they're sorted, but if you want, you could say max A, so it's just the maximum value in the data set. That did not work because the data set is now called C. So the maximum of C is 184.1. The min of C is 148. So you can quickly get those just by asking for max or min. And I'll go ahead and list those commands. Okay, so min A or max A, those are the commands we've got so far. Okay, so here, again, max 184.1 plus min 148.0. Just average them, so you add them up, divide by 2. I don't think I use Desmos for that, even though I could. So you should get 1.166.05. So that one you can easily do by hand. Any questions? So that's, I think I'll just do these in a different color, maybe put a box around it. Okay, so got that. Okay, now there's sometimes we'll have to do a mean from a frequency table. This won't happen much, and I don't know that I would do this on an exam because it's just not very important. But basically, if you look at the formula for the mean, that's X bar. And so here's the formula, the sum of X over N. Okay, and here X is my values in the values in the table here. But notice that the values are occurring with frequencies bigger than 1. So really, if a 10 appears twice, then you have to add it together, 10 plus 10, or you could just multiply it by 2. So the idea is if F is the frequency, you would multiply each of these by the frequency. And then we might add and you add them up like that. And then you might remember that N, your sample size, is the sum of the frequencies. Okay, so what I usually do for that computation is I just add another column to the table. And here you're going to see me doing the mean by hand. If it's in a table like this, we'll probably just do it by hand. Okay, so the extra row is F times X because that's what's called for here. We have to sum FX. So here 2 times 10 is 20. And 5 times 15, I don't know, 75. And 13 times 20 is 260. 8 times 25 is 200. And 6 times 3 is 18. 6 times 30 is 180. Like that. And you have to add up the F column to get the sample size. So the frequencies are 2 plus 5 is 7, plus 13 is 20, plus A is 28, plus 6 is 34. Okay, so the 34 is N. That's the sum of the frequencies, which is 34 people or individuals in this sample. Okay. And then you have to add up the FXs because the formula for the mean asks for that. So here I'm going to add up this column. I'll just go by column. So a bunch of zeros and a 5 there. 2 and 7 is 9, plus 6 is 15, plus 8 is 23. That's a 3, carry a 2. So 2, 4, 6, 7, 735. Okay, so for the sample mean, you could say X bar is the sum of fx over n. So that would be 735 over 34. Okay, which we're going to round to one place after the decimal. I'll give the rounding rule in just a moment. Okay, anybody with one place after the decimal?
Is it 21.6?
So the mean is 21.6, and that makes sense. It's kind of right in the middle of this list of numbers. The middle class goes from 20 to 24, and the mean is right there in the center of 21.6, right around 22. Okay. So that's pretty simple. And then let's add our rounding rule real quick here underneath. This will be for averages. And then later, it'll be for standard deviation also. I should spell it out. Standard deviation later. Okay, I want you to keep one place after the decimal more than the data values. Maybe I should say keep one place more than the data values. After the decimal. Okay, does that make sense? So if you look at what we did here, the mean here was 21.6. I kept one place after the decimal when the data values were all rounded to whole numbers. So that's 0 after the decimal, and I increased by 1 decimal place on the average. Same as above, the female heights were all one place after the decimal, but my average had 2 places after the decimal. Okay, now the only exception, and same thing with the mid-range, 2 places after the decimal. The only exception would be the median. I don't have a rounding rule when you're not rounding. Okay, so the 159.8 is a non-rounded value, so I don't have a problem just recording 159.8 on that. There was no rounding there. If you're rounding, then you should have one more place after the decimal than you started with. Okay, any questions about that? Okay, so we're going to do one more break until, let's say, 11:10. Let's say 11:05. And so I can't, for some reason, my stylus has died. I don't know why. Bluetooth is off, that's why. Okay, so come on, stylus. Yeah, so let's get back at 11:05. Can't write it down, but that's where we'll go. Word. Okay, so we're going to jump into 2.4 now, which 2.4 talks about measures of variability or variation. Oops. Okay. And I'm going to go ahead and look at two data sets. These are typical monthly temperatures for 12 months in two different cities. One first is St. Louis and then San Francisco. So I want to go ahead and will you guys add up the San Francisco temperatures, and I'll do St. Louis. Just add them up real quick. Yeah, I can't get it either. Okay. Okay. So I'll take, yeah.
I'm working on I'm working on Desmos right now to
Yep.
take care of all this, and I did the first part to A equals and all the stuff, all the numbers. And then for the second part, to sum everything up, I type in sum,
Yeah.
and then
I'll-
what do I do?
Let me show you what I did again.
Okay.
See if I can pull this off here real quick. I did the same thing. So you can see what I did. There are 12 numbers this time. So if you type sum, you get this symbol for summation. And again, I'm not asking you guys to ever do this. When I said add them up, I just meant add them up on your calculator, but that's okay. So I did the same thing. But I was doing San Francisco. I hope I was doing it. No, I wasn't. I was doing St. Louis. You guys were doing San Francisco, right? So regardless, let's see if we can get these numbers down here, regardless of how you did it. So for St. Louis, we'll call the St. Louis values X and the San Francisco Y. So I think I did St. Louis. So X bar is the sum of X over N. And for me, my sum was 673.2 divided by 12 months. So that's 56.1. I'm going to put an O after it. There's actually no rounding here, 56.10. Okay, and then for San Francisco, we're calling those values Y. So the mean would be Y bar. And so that'll be the sum of Y over N. So did anybody add up the San Francisco temperatures?
683.8. I'm more than likely I'm wrong.
683.8.
I got
that
that.
And it sounds like we have agreement on that. So more than likely you're right. Yeah, and then divide it by 12. And what do you get?
56.98.
Right, 56.98. So these are really similar temperatures, right? So yes, it asks if the temperatures, I'll just say the averages are almost the same. Average. Okay, so I should have said R. Okay, and so they're asking us to do dot plots. So now we're just going to plot the best we can each of these points. So for St. Louis, 29.9 is almost 30. We just do it above the graph a little. 33.9, 45.1, and so on. Okay, so I've got my dot plot for St. Louis. And then again, San Francisco. These get a little too close together. I'm just kind of cramming them in. Can't even see them all. 57. I'm gonna pile up a little bit because I'm running out of space. Okay. All right, so is it sufficient to just talk about the average temperatures for these two cities to have a feeling like you understand their climates? What do you think?
Probably not.
I mean, what's going on in San Francisco compared to St. Louis?
It's pretty consistent in San Francisco, whereas St. Louis, it's a little all over the place.
Yeah, St. Louis is all over the place. It gets pretty hot. These are average monthly temperatures, so averages don't tend to get as extreme as daily temps, like the highs or whatever. So, the average that you see doesn't go any higher than 80, but it never hits 80 in San Francisco, not as a monthly average. You have to remember they're averaging all the foggy days with the sunny days, and it's foggy just all the time in San Francisco. So, you just don't get hot days out there. Not hot months, I should say, since these are monthly averages. Okay, so right, there's just really different temperatures. So it says, does the mean temperature provide information to summarize and compare the two data sets? No, we need some measure of spread, right? Okay, so we've talked about the range. Remember, the range is max minus min, and this is a measure of spread. Okay, the max minus the min. Oh, so they're going to ask for the range for each data set above each dot plot. So for St. Louis, the range is the max minus the min. So the max for St. Louis was that 79.8 was the hottest, minus the coldest, which is I think the 29.9. That's a January coldness, 29.9. Okay, so that's about 49.9 degrees spread. You say it's a 50-degree spread for St. Louis versus San Francisco, nothing even close to that. The hottest monthly average was 62.3. Minus the coldest, looks like the 51.1. Okay, so I got, made a mistake. Anybody get that?
It's 11.2.
Thank you. So an 11, basically a 10-degree spread versus a 50-degree spread. So one climate is just much more variable than the other. Any questions about this? We talk about how, remember, margins of error are directly related to variability. So the range is almost 5 times bigger for St. Louis. So if somebody asked me to estimate the average temperature for St. Louis, I would give an average, but then I would also give a margin for error, and the margin for error would be 5 times bigger. Okay, this is just 5 times the variability is going to give 5 times the error is the principle in statistics. So we've done this next part. The weakness of range as a measure of variation is it only takes 2 data points into account. The max and the min, and they are the most extreme values, which is also a bad thing because extreme values can be suspicious sometimes. Okay, any questions about that? So range is one way of quantifying variability, but it sort of comes out bigger. It comes out too big because it only looks at the most extreme values. So a better measure of variation should consider all data points. Okay, that way you're not looking at the most extreme ones. So what we're going to do is just look at deviations. The one we're going to use is called standard deviation. And standard deviation is just the average of each value's distance from the mean. The distance from the mean is called the deviation from the mean. We just average those. Okay. So for a given value x, remember the mean is x bar. That's a sample. Well, no, let me write it this way. Hang on. Let's say the sample mean here is x bar. And then deviation from a population mean, remember the population mean is mu. That's the Greek M. It's not U, it's mu. Okay. So if X is the value, then X minus X bar is the distance from X to the mean, but that can be negative. So sometimes you have negative deviations or positive. For values below the mean, the deviation is negative. X minus mu would be deviation from a population mean. Okay, now, another little question that arises is for a given sample of values X, what do you think would be smaller on average? Deviation of sample values from the sample mean or deviation of sample values from a population mean? The sample mean comes from the sample, so it tends to be centered right inside the sample. The population mean won't be centered inside the sample. So what are the sample values closer to? The sample mean or the population mean? All right, I'll just put it down here. Sample values are closer to their sample mean. That's X bar. So X minus X bar tends to be smaller than X minus mu. And when I say tends to be, I mean on average. Okay. Okay, so we're going to do the St. Louis deviation. St. Louis, the mean was 56.1. Now that was without rounding. So here the mean is, that's a X bar, 56.1. Okay, so the deviations, this one right here is the deviations, remember, are X minus X bar. So you would do 29.9 minus 56.1, like that. So you just take each value, you subtract 56.1 to find the deviation from the mean. So again, just do that on a calculator. So first one should be negative 26.2. And you're saying that this value deviates from the mean by a distance of 26.2. It's negative, which means the value is below the mean. You do it again for 33.9. You subtract the same 56.1. And you get negative 22.2. No, 45.1. The deviations are getting smaller as the values get closer to the mean. This one's just negative 11. I'll say 0.0 just to make that clear. 56.7 is above the mean, so the deviations will be positive now. So this first one is 0.6, very close to the mean, so the deviation is small. Next one's easy, it's just 10. Next one is 19.3. Deviations are getting big again. Next one is 23.7. Next one's, yeah, next one's 21.5. Just subtracting 56.1 from all of them. The next one's 14.1. We got 2.3 now. Now they're going negative 9.9. That's because the temperatures are now below average. The coldest, and this is December, 33.9. It's not the very coldest. Minus 56.1. Again, below average, so it's negative. Here, 22.2. Okay. Now, those are the deviations from the mean. We're kind of trying to measure kind of an average of the deviations from the mean. So it makes sense to take the mean deviation from the mean right now. So you would add these up, positives and negatives. So this would be the sum of x minus x bar. Okay, the deviations are all x minus x bar. Here. So if we add those up and we divide by our sample size, which is n, okay, when you add the deviations up, did anybody do it? I don't really want to wait because we only have 10 minutes left. If you add these up, make sure you put the negatives in for the negative numbers. And when you do that, they will add up to 0 over 12. So the mean is 0. There's, on average, no deviation from the mean, which doesn't make any sense at all. But that's the mean. The mean deviation is 0. Totally useless. Okay, so the sum of the deviations is the sum of x minus x bar. And this came out to be 0. Okay. This will always happen. The mean's in the middle of the data set, and it's a balancing point. So it perfectly balances the negative deviations on the left with the positive deviations on the right. So they have to add up to 0. Okay. So I'll say the mean perfectly balances the negative and positive deviations. The below average and the above average deviation. So yeah. Deviations always add up to 0. And so then the question is, if they always add up to the same number, are they all random? Is that random if they always add up to the same thing? Seems like the opposite of random to me. You guys follow this logic?
No.
if Let's say I give you 5 numbers and you know they add up to 100. How many of them are random?
None of them.
Well,
5?
give me a number.
5 of them? Since it's 5 numbers?
There's 5 numbers. Okay, give me a number. Let's
20.
say, let's make it simple. Let's say 3 numbers. Okay, the first one's 20. What's the next one? Anything, random. Pick
50.
50. Okay, 20 plus 50 is 70. What's the third number?
30.
Oh, how many of those were random?
All 3.
Wait,
No.
you
Yeah.
had to give me a 30, didn't you?
Oh, okay. I'm getting it. It's
You
only
didn't.
2 of them.
There's only 2 that are random. Okay, so there are n deviations from the mean.
I don't get it.
If you know what numbers add up to, okay, like I said, you know 3 numbers add up to 100. So the first one was randomly a 20. Someone just picked it. The next one was randomly a 50. Somebody just picked it. So that makes 70. But you know they add up to 100, which means the third one cannot be random. It has to be a 30. Okay, so once the first 2 were picked, the last one is sort of determined. The last one is determined by the prior ones. That is always true when you know what a list of numbers adds up to. Now, deviations from the mean have to add up to 0, which tells you they are not all random. Okay, now this is super important because statistics has to deal, remember, we're going to be using probability to find out whether things are true or false. And probability is measured partly through how random the values you are that you're working with. We need to know how random our data set is. So we're going to be measuring a thing called degrees of freedom, which is out of all the observations you've got in a list, you have to tell me how many of them are random. That's called the degrees of freedom. Okay, and that will be used to determine the probability of whatever value you're getting. Okay, so I don't want to get too deep into that, but the point is there are n deviations that must add up to 0. So only n minus 1 of these are actually random. Okay, so n is sample size. N minus 1 is called degrees of freedom. Okay, which is the number of random deviations from the mean. So there's just 2 other questions. We might as well get these. So it says, is the mean deviation a useful measure of variability or scatter? And we've already seen that the mean deviation always comes out to be 0 because deviations always add up to 0. That's that predetermined sum. Okay. Does it make sense to average deviations? The answer here is no. It's always 0. So it's not useful. Okay. So how could we measure variation that uses all the deviations and doesn't always come out to be 0, I guess is the point here. And that is that we need to make the deviations positive. You can use absolute value or you can square them, okay? So we need to make the deviations positive. And again, through absolute value. Or squaring. It seems strange to square numbers, but if you square a negative, you get a negative times a negative, which is always positive, right? You multiply the number by itself. So if you square a negative number, you're multiplying a negative by itself. That will always come out positive. If you square a positive number, you multiply it by itself, it comes out positive. So squaring is sort of like absolute value. And it turns out working with absolute value, I'll just say here, this turns out to be too messy. It's not that it's never been done. People have developed theories of statistics that revolve around taking absolute value when you compute the standard, which is what's actually called a mean absolute deviation. Some people use absolute value. You have to come up with all new formulas. And squaring turns out to be tidier. And tidier means easier. So you'll see that when we do the standard deviation, like for a whole population, what we're going to do is we're going to take the deviations, x minus, now these are deviations from a population mean here. Okay, and this is called standard deviation for a population. You take the deviations, instead of adding them up, we'll square them and then add them up and then average them. Because it's a population standard deviation, I'm going to divide by the population size. So what that is that's the average squared deviation, and just take a square root to make it an average deviation. And this doesn't ever come out to be 0 unless the numbers are all the same number. Okay. I'll go ahead and just, there's more to say obviously here. We won't compute standard deviations by hand because it's a pretty drawn out computation. It's time to go. So I'll be in my office hour at 11:45 in about 4 minutes, or 5 minutes, if you have any questions for me. Okay, and have a great week. Don't forget about the proposal for your project that's due on Wednesday at midnight. That gives me a chance to read them on Thursday and get back to you next Friday. I'll see you guys.
Thank you, Professor.
Bye. You're welcome. Bye.
Thank you. Bye.
Thank you, Professor.
And just as a reminder here, sigma, this Greek letter, so it looks like a 6, but it's leaning over a bit. This is a Greek sigma. It's a lowercase. Okay, and it's for the population standard deviation. Yeah, sigma is an S in the Greek alphabet, and so obviously the S just stands for standard deviation. Now, the population standard deviation, again, comes from a big population. So when it says, can we compute sigma, what we maybe will say only for small populations where you can gather all the data. Okay. But we can do a sample standard deviation if we have a representative sample. So let me put that formula in here. So the sample standard deviation has a similar formula. I'm going to take deviations because you won't know the population mean either. We're going to take deviations from the sample mean. Okay, so instead of x minus mu, we do x minus x bar. Okay, and then we square that. Okay, and then you would divide by the number of values. But then I want to pause for just a moment and remind you of something we talked about last time before I put the denominator in. Okay, and I can put this in, the sample size in, but this turns out to be a biased estimate of S, so of sigma. I'm actually going to change this formula, so you may not want to write that down. Okay, so let me just go ahead and back up here. If you're estimating the population standard deviation, we would like to get an estimate that is not biased. Now, biased means it tends to be too small or it tends to be too large, one of the two. Okay. This one tends to be too small. Okay, let me explain. We have it here that sample values are closer to their sample mean because the sample mean comes from those values than they are to the population mean. So x minus x bar, the distance from a sample mean tends to be smaller than the distance from the population mean. These values don't produce the population mean, they are the sample, so they produce a sample mean. And the sample mean will be better centered in that sample than a population mean, which is from a lot more data. And other data will give different values and a different mean. So it's just not going to be centered exactly in this data set. So these x minus x bar values tend to be too small. Now we're still trying to estimate the population standard deviation, but we're using a sample mean to do that. Bottom line is this statistic tends to come out too small because overall the values of x tend to be closer to x bar than they are to mu. And remember, we're trying to estimate this one, which has mu in it. Okay, so to remove the bias, statisticians have learned that it is removed if you lower the sample size, which makes the result a little bigger. And the question is, well, how low should I reduce? I said the sample size. Let me change that. Statisticians have learned that you have to decrease the denominator to make the result a little bigger. Okay, we know that, but the question is how much? And it turns out that if you reduce the sample size by 1, oops, it takes care of the problem. Okay. This way. So let me delete that other formula because that's not the one that we use in the end. Okay, we use the one with the sample size minus 1. Okay, so that's the closest we can get to an unbiased standard deviation. If it's, I want to put in another note here. Also, the sample variance is another word I want you to know. So it's the standard deviation squared. Got it? And so I'm just rewriting the formula without the square root. Okay, so that's called variance. And it turns out that with the n-1 denominator, that's also an unbiased estimate of the population variance. And I guess somewhere up above, I could add that the population variance is sigma squared. And again, we don't compute these Greek letter computations. We estimate them. Okay, and again, standard deviation is the average distance from the mean. You can say average deviation, and if that's confusing, just replace it with distance from the mean. Okay. Okay, and then I'll go ahead and fill this one in. Because, and I've already explained this. So because x minus x bar values tend to be less than x minus mu, the sample standard deviation tends to be too small. Let's say smaller than the population standard deviation, which is sigma. Let me put the symbol for sample standard deviation, that's S. So the sample standard deviation S tends to be smaller than sigma. Dividing by n-1, it does best to I'll say removes this bias. Almost entirely. I'll add that the sample variance up above, this one's an unbiased estimate of sigma squared. But taking the square root introduces another bias, so that's a long story. But so I say it's almost unbiased when you divide by n-1. All right, so let's go ahead and we've got this list of St. Louis temperatures here. And I want to remind you that we computed up above here, we computed all the deviations for the St. Louis temperatures. All right, and so they're copied down here. And now remember, for the standard deviation, we have to square the deviations. So we're doing the sum of x minus x bar. We're squaring that. We're going to divide by the sample size -1 and then take a square root. Okay. So that'll be our process. Okay, so let's go ahead and start squaring these. I wouldn't put the minus signs in when you square the numbers, because if you do, if you square a negative 26.2, you technically need to put it in parentheses, like negative 26.2 squared. And you're going to get the same thing as if you square positive 26.2. So please, if you do put the negatives in, use parentheses. Otherwise, just don't put the negatives in. Let's go ahead and fill this out. Almost too small to write in. Okay, so we know that makes the squaring them makes all of these positive, which was the whole point of squaring. And then we have to add it up. So now take a moment, let's all add them up and let's see if you guys can get agree on something.
Professor,
Yeah.
3,492.02.
Okay, 3,492.32. Is that what you said?
02.
Okay, now don't forget you have to right. So I'm getting ahead of myself here. So I'm going to move this over to the side for a second because that's not the answer to the problem, but that is the total of the values. I'm going to keep, I just have a couple more to enter, so I'm going to see if I get the same as you. Or I could ask, did anybody else get that? Because I got a little different value. 64103. Darn it. 492, 98, 5.29, 98, 462, 561. I'm just kind of tapping through mine, making sure I didn't make a mistake. Yeah, so I think you're off by 100. And I need someone else to pipe in to let me know what other opinions we have here.
I got 3,592.02.
Yeah, that's what I got too. So I think, thank you. These are very error prone. I think that's a 5. Now, don't forget, that's just the sum of the squared deviations. Okay, we still have to divide by n minus 1. Now, n is the sample size. There's 12 values here, so n is actually 12 because there's one for each month. So we're going to divide this by 11. So I'll just write 12 minus 1 here, but on my calculator, I'm going to put in an 11. And then we have to do the square root. Okay, horrible, just horrible. Okay, and again, don't forget the square root. Anybody have this one? Don't be shy.
Is this one 18.07?
Yeah. Okay, 18.07. It's 0706 or so. And so you can see that there's 2 places after the decimal here. So our rounding rule will be the same that we had for averages. And that is I want you to keep one place more after the decimal than the data values you started with, the sample data. Okay, so here goes keep one place more after the decimal. Than the original sample data. Okay, any questions about that? Okay, so we would say, and if somebody asked me to interpret this, I would say that the mean, I don't know what the mean is. So the mean was 56.1. So the average deviation from the mean now the mean was 56 point, I think I said 01 degrees Fahrenheit. Average deviation from the mean of 56.1 degrees Fahrenheit is 18.07 degrees Fahrenheit. Okay, so we have a mean, but then we have an average distance from the mean or deviation. Okay, any questions? Okay, now the next part is using technology to do this because you're never going to do one of these by hand again. Not if I have any say so in the matter. So the technology is going to be desmos.com. So you go to desmos.com. Okay. And then you have to go into the graph. I think it's called graphing calculator. Okay. And then what you do is A has to be the data values in square brackets. Okay, so the we're doing the San Francisco temperatures. So let me find those real quick. Okay, here's the San Francisco. So they are 51.1, 54.4, 54.9. I'm going to do comma and then dot, 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 comma, last one, 51.7. So you got to put them all in, obviously. The dot, 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 ellipses mean just keep going. Okay. Okay, so let's do that first. So we're going to pop over to desmos.com and I'll do my share. So you just click on the graphing calculator in there. And this place where you enter commands is on the left. If we do graphs, that's on the right. I'm going to just kind of drag this over so I get lots of space here. We're not graphing anything right now. This thing does all kinds of graphs, which is kind of super cool. You just say A equals, and it has to be in square brackets. And then just put all these numbers in. Again, the San Francisco numbers, not the St. Louis. So first one's 51.1, 54.4, and I'm just going to keep typing. I encourage you to do the same. And let me know if you have questions. And you should see over on the right that A is a 12 element list. So that tells me I put enough values in. Doesn't tell me that they're right. I hit enter just to kind of register that. And then if it's an exam, for sure you want to go over this list. So I'm just double checking my values. Okay, so my values are all correct as far as I can tell. Okay, and then if you want the mean, which is not really the question right now, but you say mean and then you put A in parentheses and you get the average. So it's 56.98 here. Okay, and then standard deviation is, by the way, you can do the median here, median of A. So it just gives the median value, and 56.9 actually sounds familiar. If you want the, sometimes you want the min, so I'll just give you the command for the min. That's the smallest value. And then the max, that's the largest value. You just keep saying, you have to tell it the min of what, right? So it's the min of A, max of A, what smallest and largest values. Okay, any questions about that? And of course, we want the standard deviation, STDEV of A, like that. So it's 3.62. I'm going to square this. Let's go ahead and do variances as well. So if I type STDEV parenthesis A, close, A, close parentheses. There's a toolbar. I don't know if you can see down here. If you click on the little toolbar, there's a squaring button there. So you can just square that and hit enter. So that's called the variance when you square the standard deviation. Okay, so before I leave this page, does anybody have questions about what I did to get all those statistics? We don't do this stuff by hand, just FYI. Once is enough. Oh, 56.1.
So if they
I
then
don't
why not
know.
do that right now? Why didn't we just work on Desmos?
Oh, why don't we?
Yeah, like for the first one where we calculated everything by hand, where I didn't know what you were doing or what we were doing for that.
Are
Why didn't we
you
just-
angry? You're angry, right?
I just where we're at all. So it would have been helpful to just do Desmos because it's a little bit more understandable right now. So I'm just curious why we did everything by hand for the first one.
Well, as a math teacher, I think that I want you to be able to see that things don't just happen magically. And, I think it would be better for you to at least know what's involved. The computer is a black box. It gives answers, but it doesn't give understanding. So yeah, it's easy to know how to do it, but that doesn't explain what it is. So we understand with the standard, and what I hope you take from computing it by hand is that you averaged the squares of the deviations and then took a square root. I don't think you would have that understanding if you just got the black box to spit an answer out at you. So that's a math teacher's answer, and maybe you don't like it. Nothing personal, but I still want you to see that, at least see the computation once in your life. Statistics is really important. A lot of you guys are going to be doing statistics if you go into grad school and stuff like that. So it's important you understand. Okay. Let's go back. But the question is, again, does anybody have any question? Nahimana, I see your question here and I don't have the answer.
Okay.
So I'm sure you're right. So I will make that correction. So I appreciate it.
Okay.
But the question right now is, does anybody have any, but I'm going to leave Desmos here. Does anybody have questions about Desmos?
Yeah, I think I missed the step where you explained how you got those those values right there that equal A for the 12.
Where did I get these values?
Yeah, sorry.
It's at the beginning. Yeah, it's at the beginning of this section, which is 2.4. These are the San Francisco temperatures. It's just in the handout. So it would be on the first page of the 2.4 notes. You see that? I'll show it. I have to look for it anyway. Any other questions about the computer before I go back to the notes?
For homework to show our work, do you want us to just
You don't have
what
to
we
show your
plugged
work
in?
on these. No, you don't have to show your
Okay.
work on these. I do not want you to show your work because that means you're doing it by hand. If you're doing it by hand, you're going to make mistakes, I promise, because there's too many numbers to deal with. All right, it says no work to show. Some later on, there's some things that the computer won't do, and you have to show your work on that stuff. Okay, but not these computations. Okay, but I'm going to provide links and the commands on all of your exams. So just to let you know, on all the exams, I will always give all the formulas. I will give the links to Desmos, and I will give all the Desmos commands with an example problem on every test. Okay, so that'll be just something you can refer to. Eventually, you won't need it, but because you'll use this a lot. Okay, but this is our calculator here. So, and you can do normal computations with this as well, but just with the plus signs and minus signs and multiplication and all that. Okay, so let's go ahead and go back here, see if I can figure it out. Okay, one sec. Okay, so first of all, we think there's a mistake. It was 56.1. Thank you, Nahimana. That was the mean for the St. Louis temperatures. So let me put that in. I wrote 56 point, what we're referring to is right here. I wrote 56.01. So that's the mistake. Okay. I also wanted to put the variance in just so that you could practice that. So just real quickly on, I don't know where to squeeze it in, but for the St. Louis variance, that was S squared. So my standard deviation was the 18.0706, I think. Yeah. So I'm going to keep all the precision there and square it. I'm squaring the unrounded value. So it comes out to be 326.55 when you round it. 326.55. I want to put that in because you're computing variances, and variances actually turned out to be super important. So for now, we just view that as the square of the standard deviation. Now, for going back to Desmos, I'm just looking at that page. So the standard deviation was 3.62, rounding to 2 places after the decimal. Okay. And then right below it, I'll say the variance is S squared, which was 13.12. Okay. Now, I probably shouldn't have put notes right here, but it's too late. I'm going to add some more to this. So once you get those values in, you say mean. I'm just putting in these commands into the notes. So the mean of A, that gives X bar. Okay, and then median of A gives the median, but that's called X tilde. Okay, max min, but let's do STDEV of A. That gives S. Okay. And the min and the max, I guess we could put those min A, max A. That's sort of obvious. Okay, so, and then there's actually a question here where I would just remind you, we've computed standard deviations for St. Louis. So the St. Louis standard deviation is much bigger than for San Francisco. Okay. And so just a real quick reiteration here. If we go back up and look at those dot plots that we drew, the range, you got the St. Louis that we gave first. Okay, so the dot plot for St. Louis has values that are really spread out with a really wide range, from basically a 50-degree range. And then for San Francisco, the values are really clustered closely together here, and a range of only 11.2. So it makes sense that the average distance from the mean for St. Louis, that is, the standard deviation, is much bigger than the average distance from the mean for San Francisco. Again, that's the standard deviation. Okay, so that totally makes sense. So going back to the answer we were putting in, St. Louis standard deviation is much larger than for San Francisco. This is because St. Louis data values are much more I'll go ahead and use language like I would say by mouth, much more variable, which means spread out. Okay. Okay. Now we're gonna, so we have standard deviation now. Yay. That's a big lift to get to that. Any questions? So that's going to be our primary measure of spread. And everything is done in terms of standard deviations. It's really common to consider values unusually large or statistically significant. When there are more than 2 standard deviations from the mean, you'll see why. But right now, we have something called the usual range. Okay, if you take the mean X bar and subtract 2 standard deviations from it, this is 2 standard deviations below X bar. And this is 2 standard deviations above X bar. And that range from 2 standard deviations below to 2 standard deviations above the mean is called the usual range. Most of the values will be in that range. And you'll see more about that in a second. So for St. Louis, we have to do X bar minus 2S and X bar plus 2S. Okay, so for St. Louis, the mean was 56.1, right? So 56.1 plus 2 standard deviations, and the standard deviation is St. Louis 18.07. Same numbers, and you add. Except for that's a minus. Drat. Okay. So why don't you guys run those numbers real quick. So anybody get the low value for St. Louis?
So it's 19.96.
Yeah. And an upper limit for this?
92.24.
92.24, thank you. So that's 2 standard deviations below the mean to 2 standard deviations above the mean. It's really unusual to see values go outside of that range. And so you might notice there were no unusual temperatures. All the temperatures for St. Louis were between 29 and I think 79. I don't think it was 89. So really moderate temperatures. All temps were in this range for St. Louis. So no unusual temperatures at all. those are average monthly temperatures, so it makes sense. Averages don't tend to have unusual values, right? Averages are in the middle. So it's averages for each month. Then for San Francisco, same thing. I think we called the mean Y bar for San Francisco. Okay, and for St. Louis, we called the mean X bar. Okay, so for San Francisco, I would do Y bar minus 2 times the standard deviation there and plus. Okay, we'll have to go back here a bit. I've lost the mean. So I'm going to slide up to the very top and hope I've got it. Here we go. So the for San Francisco is 56.98. Okay. And then again, subtracting 2 and adding 2 standard deviations, which are 3.62. So we get the low end.
49.74.
Okay, 49.74. Somebody else for the upper end? Anybody?
64.22.
Good, thank you. Okay, so you see this comment here. Because of the definition of the usual range, a value is considered unusual if it's more than 2 standard deviations from the mean. Okay, and so unusual is just another word for statistically significant. And statistical significance is just super important in a statistics class. We're always looking for the significant values and trying to learn from them. So 2 standard deviations from the mean. Why 2 standard deviations? You'll see in just a moment. Okay. So here we have some historical data, sort of interesting. Now, I don't remember the dates. I think these are in the book. And the dates are from the 1920s, I think, when they were trying to estimate the speed of light, which is crazy when you think about it. And it involved shining a spotlight from the top of Mount Baldy, which is Mount San Antonio, to Mount Wilson, where there was a mirror, and they bounced the light beam very carefully, pointed the mirror to bounce it right back to the top of Mount Baldy. And then they had this spinning contraption that very cleverly figured out how long it took. And based on that, they were able to figure out how fast it was, how fast the speed of light was. And you can read about that just by Googling it if you want. But these are the first, they did it hundreds of times, but these are the first 100 estimates of the speed of light. And now these are in thousands of kilometers per second. So 299,000, 600 and whatever. Okay. So, and looks like there's a funny little colon down here, which I'm going to make go away. There we go. So the mean of the values is 299.852, and the standard deviation is 0.070. It says how many values lie within the usual range. Okay, so what we're going to do is do the usual range first. So that's X bar minus 2S. So X bar 299.852 minus 2 times 0.070. And then same thing, but adding. So just shout out the lower limit if you get it. Any questions? Any answers?
299.712.
Okay, 299.712. You guys correct me. I think the upper one is 299.992. Now, it asks how many of the values in the data set lie within the usual range. So what I'm going to do, and these are sorted from low to high to make it a little easier. I'm just going to highlight the ones that aren't in the usual range. So the lower limit is 299.712. So this first one is out. This one's out. 299.72 goes above the lower limit. So that's good. Now the upper limit is 299.992. So we're going to find out who's out. This one is out. That's outside of the usual range. This one's out. Okay, this other 300 is out. But then there's a 299.99, which is inside. It's below 299.992. Okay, any questions? Okay, so how many values are inside the usual range? Again, there's 100 values here.
95.
Yeah, so 95 values are in the usual range. And what percentage of values are in the usual range? Kind of obvious, right? 95 out of 100. So 95 out of 100 is 95% of the values. Okay, now this isn't just any random data set, and not any random data set would have done for me on this one. I needed it to be bell-shaped. So I've got a graph here of the speed of light values. And again, bell-shaped doesn't mean it's this perfect symmetric bell. It just means that it starts low, it goes high in the middle, and then it goes low again. That's what we mean when we say bell-shaped. Okay, it's nice if it's symmetric. It doesn't have to be perfectly symmetric. Okay. So bell-shaped is sort of an idealistic idea. It's not meant to say that data have these perfect smooth shapes. They don't. Okay, we just mean it's high in the middle and symmetric, roughly. Okay, any questions about that? Now, so I had to find a nice bell-shaped distribution of data for this example. We found it, and we can continue here. It says, use the dot plot above to describe the shape of the distribution. This is a bell-shaped distribution. Oops. Okay. And so finish the following sentence. So it says, in a bell-shaped data distribution, we expect about blank % of data values to lie within 2 standard deviations of the mean. What percent? Based on your empirical data. Empirical means like real evidence, right? Not theoretical, but empirical, something you can prove with evidence. So what's your evidence?
Was it 95%?
Yeah, 95% of values lie within 2 standard deviations of the mean. Okay, this is normal when you have a bell-shaped distribution. And that's why we call bell-shaped distributions normal distributions of data. Okay, so we'll spend a lot of time just learning about the normal distribution, which is the bell shape, the bell curve. Okay, and it happens a lot when we work with data, and so it's a really important thing in statistics. So 95% of the values about 95% of data values tend to lie within 2 standard deviations of the mean. If that's not true, then it's not a bell-shaped distribution. Okay, if you know the shape, you ought to be able to chop it up and describe roughly what the percentages are. Okay, it's just a function of the shape. So it's not magic. It's just chopping shapes up. Okay, if you knew it was a square, it would have different percentages, right? Or if it's a rectangle or whatever. Anyway, so why do we call it the usual range? But because it contains almost all of the values. Oops. Of course, it only contains 95% over generally. Okay. And the graph here is just this sort of beautiful distribution, a theoretical bell-shaped distribution. And just to remind you, this Greek letter mu, this is the population mean. Okay, and then sigma is the population standard deviation. Oops, I just say pop. Okay, so here in the middle of this distribution, you've got the population mean. Okay, and if you add 1 standard deviation and go down 1 standard deviation, does that capture most of the population? It does. About 68% of the values lie within 1 standard deviation of the mean. Okay, and while that's most of the values, it's not like an overwhelming majority. So when we talk about what's usual, we kind of want to say, well, the overwhelming majority of values lie within this range. And 68% is not really an overwhelming majority. It's a majority. But we wanted something where it was almost everybody. Okay, when we define what a usual range is. So 68% from that graph, this is just us chopping up a bell curve in terms of standard deviations. So here, if you go up the mean plus 2 standard deviations, that captures 95% of the values. Okay, so that's the second answer down here, about 95%. Okay, and then if you go up the mean plus 3 standard deviations down to minus 3 standard deviations, that generally is everybody. There will be exceptions when you have large groups. 99.7% of a population should be within 3 standard deviations of the mean. And again, this is called the empirical rule. Empirical just means, look, it's just what happens with data. We see it happening all the time, but only the ones that are bell-shaped in distribution. Okay. Now, I say down below the empirical, live it, love it, believe it. It's a little silly, but that second part of the empirical rule, which is this rule for unusualness, 95% of values lie within 2 standard deviations of the mean. That's almost statistics right there. You know, when we talk about statistically significant, we just mean unusual. And unusual happens 5% of the time, because 95% of the time you're within 2 standard deviations of the mean. So how do we identify these unusual values? We're just looking for values that are more than 2 standard deviations away. And almost everything we do for the rest of the semester, well, once we start statistical inference, where we're trying to kind of spot things that are significant, it gets complicated, but you can almost boil it down to, hey, we're looking for around 2 standard deviations. And if we can pull that off, we've got statistical significance. And that means I can write my research paper, or we can start selling this new medicine, you know, assuming it's safe. Okay, any questions? So almost everything builds on this notion of what's usual and what's unusual. So this super duper important here. All right, so it's 9:50. This is a computational formula for the sample standard deviation here. And you can see I'm just taking the formula for the population. I guess there's a population standard deviation computational formula. We'll never use these, so don't get panicky. But I am going to do a little talk later where I use this formula. Okay, so this is the population standard deviation here. That's the formula I gave before, and I'm just doing algebra on it, and I'm not expecting you to follow that. Or you can if you want, you know, to take the time and try and make sense of that in your head. But the point is that I'm able to develop a new formula for the population standard deviation. And then if I just do the same as before, I change the n in the denominator to an n-1, and that's the sample standard deviation. All right, so that's it for 2.4. Let's go ahead and take our break till 10 a.m. So I'll see you guys in a minute, maybe 10:01, I guess. Okay, so real quick before we go on, does anybody have any questions about anything? All right, then. So we're going to go back to section 2.5. This is a real short lesson, so it'll only take a moment to zip through this. So let's jump in. 2.5 is measures of relative position. Okay, so this is basically about trying to measure where a particular data value lies relative to the rest of the data set. I mean, is it a low value? Is it a high value? Is it near the average? That kind of thing. Okay, so there are 2 measures. One of them is called the percentile, which I think you guys are pretty familiar with. And then the other one's called the z-score. And the z-score is probably the more scientific one, and it's the one we focus on the most. But it can interact with percentiles as well, as you'll see. So they kind of go together, although it's hard to see why at first. Okay, let's jump right on in here. It says, in this lesson, we want to find a way to describe the position of a value relative to the rest of its data set. The first measure is the percentile. So the percentile of a value x is the percent of values in a data set that are less than x. And you round it to a whole number usually. To compute the percentile of a value x, use the formula below. So you just count the number of values less than x. Oops. Okay. And then you would divide by the sample size, which is n. Okay, and then you should multiply this by 100 and round to a whole number. Okay, any questions about percentile? Super easy. All right, so you've got, I think you've seen this data set a few times at this point. Their heights of randomly selected adult women in centimeters, and it's wanting the percentile for the woman who's 166.9 centimeters. I can tell these are not sorted, so let's find her. 166.9. Where's she? Right here. And then we're just counting how many women are shorter. Just count up how many are less than 166.9. So I think I'll just quickly kind of underline them as I count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 156.9, right? So 20, 166.9. So there's a 21, 22, 23. That's what I got. So it's 23 out of, I think it was 30. Yeah, so it's out of 30. You just multiply that by 100, and then we'll round off. Give me a shout that one out.
Uh, 76.66.
Yeah, so 76 point, let's say 67. But again, you need to round this off. So we're going to call this the 77th percentile. And again, it's a rounded value, but you're basically saying that this value, the 166.9, is taller than 77% of the other values. Okay, so we could say it as 77% of values are smaller than the given value, 166.9 centimeters. And so again, these are whole numbers. There's actually ordinal, so like first, second, third, 77th. Okay, that's how you do that. Any questions? Okay, and then the z-score is the next one, super easy also. There's a formula for it. Formula is sort of common sense, but we'll think about it a little bit. Says z-score, the z-score of a given value x is the number of standard deviations that x lies from the mean, number of standard deviations. So for IQ scores, the mean is 100 and the standard deviation is 15. So the question of what's the z-score of an IQ that's 130, how many standard deviations is that above the mean? So take the mean, which is 100. How many standard deviations do you have to add to get to 130?
2.
Yeah, so the z-score is 2. This is 130 is 2 standard deviations above the mean. Okay, so the z-score is 2. Okay, what's the z-score of 85? Little hint, we've said that deviations in general from the mean are positive when you're above average, and deviations below the average should be negative. Okay, so what's the score here? So again, take 100, which is the mean, and how many standard deviations do you have to subtract to get to 85?
1.
1, yeah, but we indicate it's below the mean by making it negative. Okay, so this is 1 standard deviation below the mean. Okay, so it comes out negative. Any questions?
What
Okay,
do you
so
mean C with the line in between it? What is that?
could you say that a little just, oh, the
The
Z?
Yeah, I don't
Oh,
understand.
a lot of us math teachers do that so that it doesn't look like a 2.
Okay, so
Okay?
if you scroll up, you're saying Z equals 2 then?
Yeah.
Z equals,
Yeah, so that's not a 2. Or sorry, the 2 is not a Z.
okay.
Yeah. Good question. Okay, so if you think about this 130, we have to think about how far it is from the mean. So to find out how far it is, you have to subtract the mean. So that's just a deviation right there. Okay, you take X and you subtract X bar, or mu if it's the population mean. Okay, and then so this turns out to be 30, right? And the question is, well, how many standard deviations is that when the standard deviation is 15? What you're doing is you're saying, how many times does the 15 go into 30? And of course, it's 2 times, right? So this is how we're computing z-scores. Okay, so the 130 is X. The 100 is the mean, which I think, let me see if we start off with mu. Yeah. So the 130 is the population mean, which is a mu. Okay. And the 15 is the population standard deviation, which is sigma. Okay. So the computation is pretty straightforward. You just do X minus mu over sigma. So that's just the formula for a deviation, but you're trying to see how many standard deviations that is. So how many times does the standard deviation go into it? Again, that'll come out negative if for values that are below average, just like deviations did. Okay, now if we're using a sample mean and a sample standard deviation, instead of subtracting the population mean, you would subtract the sample mean. Okay, and you would divide by a sample standard deviation here. So those are still called z-scores, and we don't really distinguish what is called. It's just a z-score either way, and then it's based on the context. If they give sample statistics, then you use X bar and S. That's all. Okay, if they give the population mean and standard deviation, then you use those. Okay. So here, there's a little problem. It says the mean of women's height is 161.4 centimeters. That's the heights above, okay? And the standard deviation is 7.73 centimeters. So we want the z-score of the woman who's 184.1 centimeters tall. So the X bar is the 161.4. The standard deviation is S. And then the individual is always just X, and X varies from person to person. So that's why it's called a variable. And so the z-score, just using the formula above, it's just X minus X bar over S. So the X value is the 184.1 minus X bar, which is 161.4. And then you see how many standard deviations that is. So you divide it in. And tell me what you get. I did a mistake. We'll keep a couple places after the decimal. Anybody get this?
Two 2.936, and then we'll add that.
Yeah, good. So let's call it 2.94. Now, is she unusually tall? And this is where you want to think about, we made a rule for what classifies a value as unusual. And remember, the z-score is the number of standard deviations from the mean. So how many standard deviations is unusual? What's the rule? Are you there? You guys there? I feel so alone right now. So back in the last lesson, there was this statement here. It says, because of the definition of the usual range of values considered unusual if it's more than 2 standard deviations from the mean. More than 2 standard deviations from mean. That could be above or below. How would we measure that? With the z-score. The z-score tells you how many standard deviations you are from the mean. So in this case, this woman, she is 2.94 standard deviations above the mean.
So it would be considered over, right? Because it's over 2.
Yeah, it's more than 2 standard deviations. Yes. So this is unusual. I'll say unusually tall. Okay, any questions? So you're just using this z-score to measure what's unusual or not. So we could, if the whole notion of statistical significance is based on how many standard deviations you are from the mean, then it's the z-score that measures that. Okay, so the z-score is sort of central to our process of determining when values are statistically significant. Okay, based on standard deviations. Any questions? That was quick, great. So that's all we do for section 2.5. It's real simple. Measures of relative position, and there's only 2 really. Okay. Now we have the next section. This one's going to be 2.6. So we're going on. So this one kind of goes off in a different direction. And the main thing we get from this lesson is something called a box plot. And a box plot is just a way of sort of showing the distribution of a data set in terms of chunks. It breaks the data set up from low to high into 25% groups. So the lowest 25, and then you have 2 middle 25s, and then an upper 25. And each of those groups are called quartiles. And then we do some stuff with the quartiles and make a graph, basically. So let me go ahead and we're going to jump right in here. I've got these randomly selected women. These, are they sorted is the question. These look like they're sorted from low to high. Just double checking. So when they ask for the median, I just want to remind you that the median is the central value. After sorting. Now, generally, I'll have you do this on in Desmos, probably. Easiest way. And I'm sort of sitting here stuck a little trying to decide, do we want to type in all 30 values? And I think I'm deciding the answer is no. The median is a central value after sorting. It looks like these are sorted. There's an even number of values. And we talked about this a little bit. If you have an even number of values, then there's two middle values. And you want to take those two middle values and take the average of them. So the middle values would be the end of the first row and the beginning of the second row. Those are the same value, 159.8. So the median will just be the average of 159.8 and 159.8. We've done this before. So you would average the 159.8 plus 159. I'm just going through the mechanics. We know that this is going to be 159.8. If they are different, which they usually would be different, you would average them. Only if there's two middle values. If there's one middle value, you just grab it, and that's the median. Okay, any questions? So that's one of the 5 numbers that we pick out that make what's called a 5-number summary. It's just basically we do 5 markers through a data set from low to high, breaking the data set up into 25% groups. Okay, so that's the middle. It separates the lower 50 from the upper 50. And what you want to do now is find the middle of the lower 50 and the middle of the upper 50, and now you have 4 groups. Okay, so Q1 is the median of the lower half of the data set. Okay, Q1, it's called the first quartile, the median of the lower half. So now I'm looking at all these numbers here, and I want to find the middle value. Okay, I think there's 15 values here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. And if you pick the 8th value and you think about it, the 8th value would have 7 below and 7 above. That's 15 altogether. So we just got to pick out that 8th value. 1, 2, 3, 4, 5, 6, 7, 8. I think it's this one. You can kind of see visually. I lost it. 1, 2, 3, 5, 6, 7, 8. You can see it's sort of right in the center of the list visually. Okay, so that's the median of the lower half of the data set. 156.8. Okay. And then the median of the upper half would be right below it in the upper half of the data set in the middle of that list. That's called the third quartile, and it's denoted Q3. So it's a 164.2. Okay, and just real quickly, I want to give you the Desmos notation for this. So just off to the side in Desmos, you would type in the list of numbers. So we're like I say, we're not doing all of them, but 148.0, 152.2, and you just keep going till you get to the last one, which is 184.1. Okay, and just to remind you, there's a command for the min, so you could say min of A. That'll give the 148.0. There's a lower quartile, the first quartile. You just type quartile A, comma 1 to tell it that it's the first quartile. And that'll give the 156.8. Okay. The median is in the middle of the list above that quartile. So if you say median of A, you don't have to say, there's no number that follows that. median of A, and you just see it'll spit out the 159.8. Now we want the third quartile, so quartile. You say A comma 3 for the third quartile, and it'll spit out the 164.2. Okay, and finally, the last of the 5 numbers will be the max, so you could say max of A. That's the largest value in the data set, and of course, that's the 184.1. Okay, now you don't have to sort the values. Desmos knows how to do that. Okay. Any questions? So again, these dividers divide the data set up in, there's 5 dividers, but it makes 4 groups. So, you know, if you want a sort of a picture of this, you have all these data points here. Okay, the min, the max, okay, the first quartile Q1, the third quartile Q3, and the median. There's a question here. It says, what's the second quartile? And we want to take a guess at that. It's a divider, and it divides the bottom 50 from the upper 50. What's that? So the notation would be Q2, and what is it?
The median.
Yeah, the second quartile is the median, which is X tilde, I guess. So we don't generally call it the second quartile, but it is the second quartile. So just FYI, in case you see that somewhere. Okay. Now, it says that 50% of the data values that lie between the first quartile and the third quartile. Again, these are each of these intervals is 25% of the data. So from the first quartile, I think I'll go ahead and do this in a darker color here. So this range here in green is the inner quartile range, okay? And it's just the distance from Q1 to Q3, 50% of the data. So the formula is Q3 minus Q1. Okay, and so for the women's heights, Q3 is 164.2 minus Q1, which is 156.8. So what's that?
$7.4.
Yeah, 7.4, correct. Okay, so that's the interquartile range. It's the width of the middle 50%. It's sort of a stand-in for the standard deviation, but it doesn't use the extreme values of the data set. If the standard deviation has a weakness, it's also sort of its strength, but it can be a weakness. The standard deviation, we liked it because it measures variation and it takes every value into the data set into account. Okay, every value in the data set. Now that's great as long as there are no weird outliers in your data set. Now, if you have a really big outlier in a data set, then that's going to make the standard deviation really big. And so the standard deviation gets influenced by sort of extreme values, which is not always what you want. The IQR stands in for the standard deviation, but it doesn't ever look at the extreme values. It just looks at the middle 50% of the data. And it's not going to be that different in value from the standard deviation, but it will be smaller than standard deviation if there are some extreme values in the data set. So we like working with medians in general because they're not influenced by outliers. And the IQR is a measure of spread that doesn't take outliers into account and cannot be influenced by them. So in a sense, it's a stand-in. And when we determine how you classify an outlier, we don't do it with the standard deviation, because the standard deviation is influenced by outliers. So if you're going to spot an outlier, you don't want to take the outlier into account as you look for what a normal amount of spread is. So we use the interquartile range to determine outliers. Anyway, so you've got this thing called a 5-point summary. Sometimes it's called a 5-number summary. So I've listed them. The min was 148.0. The first quartile was 156.8. Okay, the median is 159.8. The third quartile is 164.2. And then the max is 184.1. So those 5 dividers make the 4 groups, which are each 25% of your data set. Okay. Now, we're supposed to do a graph that's based on these. And we haven't done the fences yet. So this graph includes fences. So I've got to define the fences, but you can see the basic ideas for this graph. But by the way, does anybody have any questions before I start doing the graph? Okay, so the graph's just a kind of representation of the 5-number summary, but it excludes outliers. Okay, so and ignore the fences for a second. On the left tip, this is called a whisker. It's called a box and whisker plot sometimes. So it's sort of like a bunny rabbit. It's got whiskers, super cute. Okay, and the whiskers go out to the highest value or the lowest value that aren't outliers. And if there is an outlier, you can see we draw outliers with asterisks. Okay. Outliers are determined by fences. Okay, so the fences are represented with these dashed lines. Anything that goes past the fence is an outlier. We don't usually include the fence in the graph, but I put it there just for you to kind of visually see how the outlier goes out past the fence. Okay, so again, these outliers need to be determined by a measure that's not influenced by outliers. Okay, so we use the interquartile range. Now, if you remember the usual range, that was this 2 standard deviation rule, right? Anything within 2 standard deviations from the mean is the usual range. Now, you can think of the interquartile range is the width of the box here, okay, because it's the distance from Q3 to Q1. Okay, and the interquartile range, the width of it is 1 interquartile range. So you could break that box in to like basically a half of an IQR, not exactly, but about a half of an IQR on the right side of the box. That says 0.5 RQR. Let me make that just a 1/2. And about 1/2 of an IQR on the left of the box. Just splitting it into 2, assuming the median is in the middle, which it won't always be. Okay, and if you look from the median, we are going approximately 2 interquartile ranges, a half of an interquartile range that's part of the box, and 1.5 interquartile ranges up from the edge of the box. Okay, and so altogether, that's about 2 interquartile ranges, just like we would go up 2 standard deviations to determine an unusual value, and that came from the empirical rule. This is sort of stealing from the empirical rule. We're going up 2 interquartile ranges from the median to determine the outlier, or we could say you're going up 1.5 interquartile ranges from the 3rd quartile, which is the edge of the box. So I'm going to clean up some of this graph real quick and just put down what I've said. Here, the lower fence, you've got to go down from the 1st quartile. You want to go down 1.5 times the interquartile range. And that'll take you to about 2 interquartile ranges below the median. Just like we would say 2 standard deviations below the mean for the standard deviation. And for the usual range. Okay, for the upper fence, we go from the right edge of the box, Q3, and we go up about 1.5 times the interquartile range here, which is about 2 interquartile ranges above the median. Okay. So now that's the rule. Let's go ahead and do the lower fence and the upper fence. So the lower fence for the women's heights, again, the formula is Q1 minus 1.5 times the IQR. And the upper fence is Q3 plus 1.5 times the IQR. Okay. Okay, so going back, Q1 was 156.8 minus 1.5. I think the IQR was 7.4. I'll double check. Yes. And then Q3 was 164.2. And we add 1.5 times the interquartile range. And those are fences for outliers. Anybody get a lower fence? Or an upper fence?
For the lower fence, I got 145.7.
Thank you. Anybody else get an upper fence?
$175.3.
Thank you. Okay, and then they use these to determine outliers. So now I have to go back to the data set, 145.7 to 175.3. If you notice, these 3 values are all bigger than 175.3. The 3 highest values. There are no outliers on the low side. Okay, so this is these guys, these 3 are outliers. Any questions? And you'll see that when we graph them, they're just really separated from the rest of the data set.
Wait, I have a question.
Yeah.
Okay, so I'm following, but right now what we're currently looking for both the lower and the upper fence is any numbers that go below 145 and above 175?
Yeah, it was below 145.7 or above 175.3, correct? You okay?
Yeah.
It's like these are fences, and it's like if you hop the fence, now you're running around wild, you're an outlier. Okay, so we had 3 renegade outliers here because they're all bigger than the 175.3. I want to go ahead and show you the graph. We've been using these data all through our talks. So I'm going to go back to chapter 1 notes and see if I can find that. Would be way in 1.1. This is the data set. Okay, so these are the same heights. And remember, there's these 3 women that were just really tall. And those 3 are the outliers. Okay, but the shortest woman was not separated enough to be considered an outlier. Okay, is there any question about that? So the math is just spotting these values. Okay, rather than having a visual assessment, we have this really objective way of determining them. Okay, any questions? Okay, so we now, yeah, there were 3. So again, I'm going to copy these down. They were 175.9, 176.4. And then the 184.3 or 0.1. Okay, so these 3 are outliers. And I just really separate it. Okay, any questions? I think there's also a rule that says if anything's more than 3 interquartile ranges from the edge of the box in the box plot, those are called extreme outliers. We're not going to bother with that here. Okay, now it's asking us to sketch the box plot on the graph down here. I'm going to go ahead and put my outliers with asterisks. So there's the 184.1 here. Okay, the outliers don't get to be part of the box plot. They just get asterisks. And then the 176.4 going to be about here, I think. And then the 175.9 is real close to that one. Okay, so those 2 just right next to each other. Now we have to put in, I'm going to put dots in here for the rest of the 5-number summary. So I don't know, I think I'm going to copy those down. So this is the 5-number summary. I'm just copying this down. Okay, so the 148.0 is easy enough. I'll just do a dot there and that'll be part of the graph. Then there's the 156.8, which is almost 157, right here. 159.8, almost 160. 164.2 back here maybe. Okay, so I'm not going to put the last point on. Let me go ahead and try my box. That looks horrible. I'll try it again. Come on.
Why are you drawing in the dot for 184.1? I mean, I understand that we have an asterisk right there, but
Could you explain again what was the question? I didn't hear very well.
yeah, why aren't we putting a dot for 184.1? Does the asterisk just
Yeah, we put, if you look at what the graph looks like, outliers here, You want to
Yeah.
graph those with asterisks.
Yeah.
Why?
No, it's okay. I understand. Thank you.
We just sort of say, these are the weirdos, and they're sort of throwing all of our numbers off. We're not saying they're not part of the data set. We're just saying they're extreme. They're sort of unexplainable because of how extreme they are. We don't want to pretend they're not there. We're going to put them in with asterisks, but we're really trying to describe the distribution of the data values that aren't extreme when we do a box plot.
Yeah, I understood that. I was just
Okay.
wondering why we didn't put a dot right there too, but I guess I understand.
Well, and there were 3 outliers, right?
Yeah.
So I have one more dot to do. Remember, the whiskers go from the lowest value that's not an outlier to the highest value that's not an outlier. Well, there's no outliers on the left, but I didn't make a note of whatever the highest value is that's not an outlier. So I have to get that. Maybe I'll do that while I'm talking about it. So going back to the data set, if I just kind of point this out here, this 170.4, that's the highest non-outlier. Okay. So that ends up being the right side of the whisker, 170.4. So I'm going to put this down. 170.4. And so I'm going to put it right back here. Okay, so this guy right there is the highest non-outlier. Okay. And so just maybe adding more, this is Q1. Sorry, no, that's the min. Right here was Q1. The 160-ish, I guess it was 159.8, that's the median. Okay, the 164 point something, again, that's the highest. Nope, that's Q3. The other one's the highest non-outlier. I'm just going to go ahead and bend my box to this graph real quick here. That's good. And then there's a vertical line drawn at the median, like this. Okay, and then we do the whiskers down to the min, or the lowest value that's not an outlier, and then the highest value that's not an outlier. And then I'm going to get rid of that curly brace there. There were 3 other values, but they kind of get kicked out of the club. They're outliers. They hopped the fences. Shame on them. Distribution is skewed to the right because you have the outliers on the right. Okay, how do you feel? Is that a loaded question? Are there any questions?
So when we're drawing this box or this graphic for the box plot,
Mhm.
you want us to include the highest non-outlier?
Well,
the
you don't have
whisker?
to label it. You don't have to label it, but the whisker has to stop at the highest non-outlier. Don't forget, there can be outliers on the left too. So the left whisker stops at the lowest non-outlier. So I could put that here. This value, the min, because there are no outliers on that side, that's the lowest non-outlier. Now you don't label it. I'm labeling it for you guys so you understand. Okay, but the graph tends just to be the box, the 2 whiskers, and then some asterisks.
Thank you.
Yeah. Any questions? Okay, there's a couple of other statistics that I have in this section, and I'm going to give the formula. I don't think I'll have you compute these ever because they're a little bit of a pain to compute, but I want to go ahead and these words come up in the book. So there's a measure, a statistic called skewness. There's a sample skewness, and there's also a population skewness. Skewness is a measure of symmetry. Okay. So just a real quick kind of a sense, this is a skew left distribution. Okay, and then maybe a skew right distribution. And then there's a nice symmetric distribution. Okay. Roughly symmetric. Okay, and all I want you to know right now, skew left is also called negatively skewed because the sample skewness, when you do the computation, it'll come out less than 0. So we have, again, objective measures for almost everything in statistics. Skewness is a statistic that measures symmetry. So the sample skewness is positive when a distribution is skewed right. So sometimes we call that positively skewed. Okay, and what do you think the skewness is for a symmetric distribution?
It's skewness less than 0 or positive 0.
Right, but it's not skew left or skew right. So what kind of falls in between those?
0.
Equals 0.
Yeah, so the skewness is, let's say approximately 0. Nothing's perfect, okay? So I'd say if the skewness comes out almost 0, then you can say, well, that's almost a symmetric distribution. Okay, the most perfect symmetry will have a skewness of exactly 0. Okay, so that's how we measure skew and symmetry. Are there any questions? And the bigger the skewness is, the more skewed it is. So it helps us find, say, ooh, if the skewness comes out real positive and big, you think, oh, God, there's got to be some outliers in that data set. So it's a numerical way of sort of realizing that that's out there. Okay, any questions? So again, I don't think I'll have you compute that, but just to let you know, that's a thing in statistics. And we'll be talking about the normal distribution, which is the symmetric one. And with a normal distribution, the skewness is equal to 0. The normal distribution is the perfect bell curve that's sort of ideal in statistics that we talk about. Any questions? Now, there's another thing that's important with regard to the bell-shaped distribution. So I'd say kurtosis is mostly for bell-shaped distributions or distributions that have tails and a high middle. So this mostly is in the context of bell-shaped distributions. We talked, and I'll go ahead and show you this. I'm so fond of it. I guess I'll show it to you. At the end, was this at the end of chapter 1? No, it was not. Somewhere in the chapter 2 notes, I'm thinking it would be right at the beginning. Here we go. We had this discussion of short tails and long tails. So when the distribution has short tails, it's like a platypus. And that's a lovely picture of a platypus with short tails. And we call that platykurtic, like a platypus. And then the kangaroos, nose to nose, are leaping about. So that's called leptokurtic. Okay, so long tails, leptokurtic, short tails, platykurtic. Okay, and if it's in between, we call it mesokurtic. Okay, and mezzo is sort of music. It's Italian really for medium. Okay, so under kurtosis, we have the short-tailed distributions like that. And that's platykurtic. And then we have medium tails. And that's mesokurtic. And then we have long tails, and the longer the tails get, the skinnier the peak is relative, because you're moving data out into the tails. So it sort of deprives the peak of data. So that's leptokurtic. Okay. And as you can see, the peak gets narrower as the tails get longer or heavier, they say sometimes, like a kangaroo has heavy tails, but the platypus has really light tails. So kurtosis really focuses on the peak. So it's a measure of, here comes a word that's not really a word, peakedness. Right? So with the platykurtic, we have a wide peak. Okay. Mesokurtic, we have a sort of a moderate peak. And then leptokurtic, we're going to have a narrow peak. How do I squeeze that in? Sideways. Okay. That says narrow. And so the kurtosis measures this. And the mesokurtic, this is a normal distribution. Okay. Mesokurtic, the kurtosis is 3. Let's say about 3. Okay, so 3 is sort of the central value for kurtosis. And when the kurtosis is less than 3, then you're talking about a platykurtic distribution. And if it's greater than 3, then it's a kangaroo leptokurtic. Okay. So just keep in mind the kurtosis equals 3 is sort of the ideal when it comes to bell curves, and the class is kind of all about bell curves eventually. So that becomes sort of a central value for us. So if you can try to remember that, that would be great and helpful. Okay, any questions about all that? I think that's the end of that chapter, right? Okay, so I'm going to stop the recording.